बच्चों अब हम चैप्टर नंबर 1 इलेक्ट्रिक चार्जेस एंड फील्ड्स की समरी पढ़ेंगे। उससे आपको पूरे चैप्टर का आइडिया लग जाएगा। इलेक्ट्रिक एंड मैग्नेटिक फोर्सेस डिटरमाइन द प्रॉपर्टीज ऑफ एटम, मॉलिक्यूल्स एंड बल्क मैटर. From simple experiments on frictional electricity, one can infer that there are two types of charges in nature and that like charges repel and unlike charges attract. By convention, the charge on a glass rod rubbed with silk is positive, that on a plastic rod rubbed with fur is then negative. Conductors allow movement of electric charge through them. Insulators do not. In metal, the mobile charges are electrons. In electrolytes, both positive and negative ions are mobile. Electric charge has three basic properties: quantization, additivity, and conservation. Quantization of electric charge means that total charge Q of a body is always an integral multiple of a basic quantum of charge, that is Q is equal to Ne, where N is 0 plus or minus 1, like this. Proton and electrons have charges plus E minus E respectively. For macroscopic charges for which n is a very large number, quantization of charge can be ignored. Additivity of electric charge means that the total charge of a system is the algebraic sum, that is a sum taking into account proper signs of all individual charges in the system. Conservation of electric charge means that the total charge of an isolated system remains unchanged with time. This means that when bodies are charged through friction, there is a transfer of electric charge from one body to another, but no creation or destruction of charge. Next is Coulomb's law. The mutual electrostatic force between 2 point charges Q1 and Q2 is proportional to the product Q1 Q2 and inversely proportional to the square of the distance R21, separating them mathematically. F21 is equal to force on Q2 due to Q1, that is equal to K Q1 Q2 upon R21 ka square R cap 21, where R cap 21 is a unit vector in the direction from Q1 to Q2 and K is equal to 1 upon 4 pi epsilon naught is a constant of proportionality. In SI units, the charge unit of charge is coulomb. The experimental value of the constant epsilon naught is equal to 8.854 into 10 square minus 12 coulomb square per Newton per meter square. The approximate value of K is equal to 9 into 10 to the power 9 Newton meter square per coulomb square. The ratio of electric force and gravitational force between a proton and an electron is given by Ke square upon G Me MP, and that is equal to 2.4 into 10 to the power 39. Superposition principle. The principle is based on the property that the forces with which two charges attract or repel each other are not affected by the presence of a third additional charge. For an assembly of charge Q1, Q2, Q3, the force on any charge, say Q1, is the vector sum of the forces on Q1 due to Q2 and forces on Q1 due to Q3 and so on. For each pair, the force is given by the Coulomb's law for two charges stated earlier. The electric field E at a point due to a charge configuration is the force on a small positive test charge Q placed at the point divided by the magnitude of the charge. Electric field due to a point charge Q has a magnitude Q का magnitude upon 4 pi epsilon naught r square. It is radially outwards from Q if Q is positive and radially inwards if Q is negative. Like Coulomb force, electric field also satisfies superposition principle. An electric field line is a curve drawn in such a way that the tangent at each point on that curve gives the direction of electric field at that point. The relative closeness of field lines indicates the relative strength of electric field at different points. They crowd near each other in regions of strong electric field and are far apart where the electric field is weak. In regions of constant electric field, the field lines are uniformly spaced parallel straight lines. The some of the important properties of field lines are continuous curves without any breaks. Two field lines cannot cross each other. Electrostatic field lines start at positive charges and end at and at negative charges. They cannot form closed loop. An electric dipole is a pair of equal and opposite charges q and minus q separated by some distance 2a. Its dipole moment vector p has magnitude 2pa and is in the direction of dipole axis from minus q to q. Field of an electric dipole in its equatorial plane, that is a plane perpendicular to its axis and passing through its center, is the distance r from the center, and that is equal to E is equal to minus p upon 4 pi epsilon naught 1 upon r का square plus a का square का 3 by 4 raised to the power 3 by 2, that is equal to minus p upon 4 pi epsilon naught r का cube, where A is much smaller than R. Dipole electric moment on the axis at a distance r from the center is given by E is equal to 2pr upon 4 pi epsilon naught r square minus a square का whole square, that is equal to 2p upon 4 pi epsilon naught r cube, where A is much smaller than R. The 1 upon r cube dependence of dipole electric field should be noted in contrast to the 1 upon r square dependence of electric field due to a point charge. In a uniform electric field E, a dipole experiences a torque given by torque is equal to P into E, but experiences no net force. The flux delta phi of electric field E through a small area segment delta S is given by delta phi is equal to E delta S. The vector area element delta S is equal to delta S n cap, where delta S is the magnitude of the area element and n cap is the normal to the area element, which can be considered planar for sufficiently small delta S. For an area element of a closed surface, n cap is taking to be the direction of outward normal by convention. Gauss law. The flux of electric field through any closed surface S is 1 by epsilon naught times the total charge enclosed by S. The law is especially useful in determining electric field when the source distribution has simple symmetry. Thin, infinitely long straight wire of uniform linear charge density lambda is equal to E is equal to lambda upon 2 pi epsilon naught r n cap, where r is the perpendicular distance of the point from the wire and n cap is the initial radial unit vector in the plane normal to the wire passing through the point. Infinite thin plane sheet of uniform surface charge density sigma is equal to E is equal to sigma upon 2 epsilon naught n ka cap, where n cap is a unit vector normal to the plane outward on either side. Third is the thin spherical shell of uniform surface charge density sigma is equal to E is equal to Q upon 4 pi epsilon naught r square r cap, where capital R is smaller or equal to small r. E is equal to 0 when r is smaller than capital R, where r is the distance of the point from the center of the shell and capital R is the radius of the shell. Q is the total charge of the shell. Q is equal to 4 pi r square sigma. The electric field outside the shell is as though the total charge is concentrated at the center. The same result is true for a solid sphere of uniform volume charge density. The field is 0 at all points inside the shell. There is a table. You have to learn the table and their physical quantities, symbols, dimensions, unit and remarks. Okay, and then read the points to ponder.